we recall this Euler formula which we are using regularly. Replacing x with minus x, we of course get this equation. Using that the cosine of minus x is equal to cosine of x, and that the sine of minus x is equal to minus sinus of x, we obtain by adding these two equations to each other this equation. You see that sine term is vanishing. So dividing with 2, we obtain this formula for cosine x. Similarly, by subtracting these two equations from each other, we obtain this identity, and by dividing with 2i, we obtain a similar expression for sine of x. This is a motivation for the generalization of sine set for complex and cosine set for complex values of set. So we just replace in these two formulas set x with set. So this is the definition of cosine and sine in the complex case. It's easy to see that both cosine and sine are entire functions. That is, that they are differentiable or analytic, if we want, in all points in the complex plane. And this is due to the fact that both these two functions are differentiable. Note that we have more or less the same formulas in the complex case as we have in the real case. Sine of the negative value of set is equal to minus sine set, and this formula is also very familiar. We have the same formula for sine of the sum of two set values as we have in the real case for both cosine and sine. So the usual rules holds. Also this general rule that the square of cosine plus the square of sine is equal to 1. This also holds for any value, complex value of set. The sine of the of 2 set is equal to this, exactly as in the real case. You also have these formula, and for example, if you want to add pi half to the argument of set, you obtain that sine of this is equal to cosine. The tangents of set is in the same way equal to sine over cosine. Here is some formula which is very useful. Sine set can be described by sine and cosine of x, and cosine hyperbolicus and sine hyperbolicus of y in this way. We are not going to use this so much. Here, recall these formulas for cosine hyperbolicus and sine hyperbolicus. We also use this formulas in the complex case for cosine hyperbolicus and sine hyperbolicus.